In this video, we are going to talk about what the method of Lagrange multipliers is, and how do we use it in max and min problems where we have a constraint. So I want to begin with an example to motivate this method. So I want to find the points on the curve x squared times y cubed equals 1 that are closest to the origin. Okay, so to get started here, just to visualize this, if I were to draw some axes, let's draw an x-axis and draw a y-axis. If I draw the graph of this curve, it turns out that it has this sort of shape. So it has this sort of portion in the first quadrant with an asymptote, a vertical asymptote at the y-axis, and a horizontal asymptote at the x-axis. And there's a symmetric portion to that on the flip side of the y-axis. Okay, so that's the graph of x squared y cubed equals 1. And what we're trying to do is we're trying to identify what point on this curve, let me just draw a point and call it x comma y, what point on this curve is closest to the origin. So if I want that point to be closest to the origin, I'm trying to make this distance from the origin to that point as small as possible. So our goal is to minimize in this question, to minimize the distance from the point x comma y that's on the curve x squared y cubed equals 1 to the origin. Okay, so the quantity that I'm trying to optimize, in this case it's the distance, we commonly refer to that as the objective. So the objective, I'm just going to write it down, is the quantity that we want to either maximize or minimize depending on the context of the problem and what the problem is asking for. So this question, our objective is d, it's the distance. So let's write an equation for this objective. So the distance between the point x comma y and 0, 0, using the distance formula, would be x squared plus y squared being square rooted. Okay, so we want to minimize this function here, but we have an additional constraint that we must make sure that we satisfy. And that additional constraint is this point x comma y is on the curve x squared y cubed equals 1. So our constraint is that the point must satisfy this equation, the equation of the curve. Okay, so there's an important observation that I want to note that's going to make our computation a little bit easier. So when we try to minimize a square root function like this, the square root of some stuff, the key observation is that d, the square root function, is minimized when d squared, and d squared would get rid of the square root and just leave us with the stuff inside the square root, when d squared is minimized, when d squared is as small as possible. Okay, so I want to just look at a few numbers to kind of illustrate why, if we're not convinced. So for example, so d in this case, because it's the square root of some stuff, is going to be a non-negative number. It's going to be greater than or equal to 0. Okay, so I'm going to look at some examples of what d squared might be. So d squared is going to represent whatever's inside the square root. So let's say that d squared is 9, and maybe it's 21, and 13, and 8, just looking at some different values. So if that was the case, if that's what d squared was, then d, the square root of these values, would be, so the square root of 9 would be 3. I don't have to worry about plus or minus, because I'm assuming that d is greater than or equal to 0 here. And the reason why I'm assuming that is d is the square root of some stuff, and the square root of some stuff can't be a negative number. The way the square root function is defined, it always outputs the non-negative value. Okay, so 21, well, the square root of that would be square root of 21. For 13, its square root is square root of 13. And then finally for 8, its square root is square root of 8. Okay, so looking at these values, the smallest value of d is square root of 8, and that corresponds to the smallest value of d squared. The smallest value of d squared is 8 in this example. So the smallest d corresponds with the smallest d squared. So the key takeaway from that is, if I'm trying to minimize this square root function, we might as well, I'm going to call this the new objective, we might as well just square that thing and look at the inside of the square root and try to minimize that. So if I square both sides, I get d squared equals x squared plus y squared. And I am actually going to try to minimize this function. Because if I can minimize this, the values that I get, the x and the y values that minimize this, are also going to minimize the square root of this thing. Okay, so I'm going to do this in two ways. So method one is going to be, how would we sort of do this using our previous knowledge? So we could substitute the constraint into the objective to eliminate one variable. So you might remember from calculus, when you did optimization questions, this was typically the strategy. Usually the function that we wanted to maximize or minimize, in this case it's x squared plus y squared, was often in terms of more than one variable, typically in terms of two variables, and we used some other information that I'm calling the constraint to plug in, to substitute into the objective equation and get it in terms of one variable so that I could take its derivative. Okay, so if we do that here, we end up getting, so if I use x squared y cubed equals 1, our constraint, so let's isolate one of the variables. Y cubed, if I isolate it, is 1 over x squared, and if I cube root both sides, we'll get y equals cube root of 1 over x squared. The cube root of 1 is just 1, and if I cube root x squared, I get x to the 2/3. I'll write that 2/3 a little better, 2/3. Okay, so now let's substitute. Let's substitute this into the objective. So we will substitute, we'll get d squared equals x squared plus y squared. So y I know is 1 over x to the 2/3. So let's substitute that in. So we'll get 1 over x to the 2/3 being squared. Okay, so this gives me, I still have x squared in the front. And then plus 1 over x to the 2/3. 1 over x to the 2/3. This is x to the negative 2/3. And if I square that thing, I'll have a power, the negative 2/3 power, and then to another power, the squared. And the exponent rule, when you have a power to another power like that, is you multiply them. So that'll give us x to the negative 4/3 when you multiply the negative 2/3 times the 2. Okay, so we have this function. It's in terms of one variable now. And at this point, we could find the max and the min using calculus techniques. So by calculus techniques, I mean stuff that you would have learned in your first calculus class. Things like taking the derivative, finding critical points, and then testing those critical points to see if they correspond to an absolute max or an absolute min. Okay, so I'm not going to carry that all the way through. I want to state what the key takeaways are from this method and why we might want a different way to do this. Okay, so when our objective is in terms of, so first off, when it's in terms of two variables, like ours was, we could get it in terms of one variable. I'll just say one var, I'll just abbreviate variable, with the constraint. So just like we did here, we could use the constraint to substitute in to the objective to eliminate one of the variables and get the objective in terms of now one variable. And after we do that, we would use calculus. We take the derivative, find critical points, test those critical points to see if they give us a max or min. Okay. And this method, it can work, and if we did it for x squared plus x to the negative 4/3, it would work, it would give us an answer. But depending on our objective and our constraint, this can be quite tedious. In this example, I would say it's actually not that tedious to do, but it can in practice be quite tedious. Well, what if we had a function where our objective was in terms of 3 variables? Well, then we could get this in terms of 2 variables with the constraint, assuming we just had one constraint equation. And then if we had a function of 2 variables, well, we've talked about how to find the absolute max and the absolute min of 2 variables in the previous section. We would use section 14.7 methods for finding an absolute max and an absolute min of a multivariable function. Okay, but as we saw in section 14.7, that's even more tedious than trying to find the min or the max of a one variable function like we did in calculus. So that's even more tedious, doable, can be doable, but it's more tedious. So overall, the more variables that we have, the more tedious using multivariable absolute max and absolute min methods would get. So we would like an alternate method. We would like an alternate method. Okay, so that's what I want to talk about next. How do we motivate this alternate method? All right, so let's let the distance, technically it's the distance squared that we're looking at right now. I'm going to call this f of x comma y. It's a function of 2 variables. And the distance squared was x squared plus y squared. So I'm just going to assign a function name to it, called f of x comma y. And we want to minimize f when restricted or constrained, when restricted to the curve x squared y cubed equals 1. So drawing a picture of this again. So if I draw my axes, got my x-axis, my y-axis, this curve looks something like this. Looks something like this. So this is x squared y cubed equals 1. And what I'm trying to do is I'm trying to find the point on this curve, or maybe it's more than one, the point or points that are closest to the origin. So the way I can sort of think about this conceptually is, what if I just started to draw circles that are centered at the origin of growing radii? So maybe I'll start with a circle with a small radius. And all the points on this circle are the same distance away from the origin. But it's a smaller distance than the closest distance from the origin to the curve, because this circle hasn't intersected the curve yet. So right now this is too small. So whatever our closest point is, it's not on the circle. Closest point is not on this circle. This circle is too small. So let's draw a slightly bigger circle. If I enlarge the circle a little bit, enlarge it a little bit, it's closer. This is closer to intersecting the curve, but still not quite. Still not quite there. So it's not on this either. So what I would have to do is I would have to make it just ever so slightly larger. Ever so slightly larger. So it just grazes the curve ever so slightly there at a point. And just by symmetry, it'll also graze it on this side. My picture is not perfect, so it looks a little bit off here, but just imagine that it is perfect. Okay, so we have this circle, and it's intersected that curve twice, just ever so slightly. So another way to say that is when the circle first touches the curve x squared y cubed equals 1, so the radius first gets large enough to just ever so slightly touch it, they are tangent. So notice that the circle and the curve are tangent at these points of intersection. If I were to draw the tangent line to the circle at this point, and the tangent line to the curve at this point, they'd be the same line. Okay, so the idea that I'm going to use is, when we think about these circles, we can think of them as being level curves of the function f of x comma y. Because f of x comma y was x squared plus y squared. And if we start setting x squared plus y squared equal to something, to different values, we get different circles. So these circles are level curves of our multivariable function. Okay, so one of the things that we know when we talk about the gradient of a function is the gradient of f would be normal to the level curves. It's perpendicular to the level curves. So it's normal to the circle. Okay, if we think about the curve x squared y cubed equals 1, this is also a level curve of some function. This is the level curve of sort of the function g of x comma y that's defined by, if I were to move the 1 over to the left-hand side and just get one side equal to 0, we get the function x squared y cubed minus 1. It's actually a level curve of this function when g of x comma y equals 0. If I set g of x comma y equal to 0, we get this equation x squared y cubed equals 1. Okay, so I also could have moved the x squared y cubed over to the right-hand side and gotten 1 minus x squared y cubed and said, oh, it's the level curve of that function when you set g of x comma y equal to 0. It would be the same thing. Okay, so in the same way, the gradient of g is going to be normal to this level curve, x squared y cubed equals 1. So the conclusion from this is, since the level curves of f and g are tangent, this means that their gradients both point perpendicularly to the curves at this point of tangency. So because the curves have the same tangent line, it means their gradients, because they're both perpendicular to that tangent line, should be parallel. They're either going to be in the same direction or opposite directions. So how do I express that with an equation? We would say that the gradient of f equals some scalar, which I'm going to call the Greek letter lambda, which is written like this, times the gradient of g. Okay, where lambda is a scalar. So if you haven't seen this symbol before, I'll just write it down. This is a Greek letter, and it's written lambda. Lambda. Okay, so our idea is going to be, now that we have this equation here involving gradients, we will solve this to find possible min and max points. Okay, so this is going to constitute our second method here. Okay, so our method 2 is going to be to solve this equation, gradient of f equals lambda times gradient of g. And the process of doing this we refer to as the method of Lagrange multipliers. The method of Lagrange multipliers. And this scalar lambda, this is called the Lagrange multiplier. We are multiplying by this number. Okay. Okay, so I'm going to highlight this equation here. All right, so let's do this. So let me begin by writing down what our function f of x comma y was. It was x squared plus y squared. We had already written down our function g. G is the function that you get from taking your constraint and rearranging it so that everything is on one side and the other side equals 0. So g of x comma y equals x squared y cubed minus 1. So technically with g, we don't have to take our constraint and set it equal to 0 necessarily. It could be equal to a different number, as long as it's a constant. But typically the convention with Lagrange multipliers is to rearrange it to make that constraint be equal to 0 on one side. So I'm going to follow that convention. Okay, so we have these two functions, and let's take their gradients. So the gradient of f is a vector. First I take the partial with respect to x, which is going to be 2x. Then the next entry is the partial with respect to y, which is 2y. And then it stops there because this function is just a function of two variables. So now I close my vector. So let's do the same thing with the g. The gradient of g, first the partial with respect to x would be 2x y cubed. And the partial with respect to y would be 3x squared y squared. Okay, so now let's set the gradient of f equal to lambda times the gradient of g. Okay, so when we do this, the gradient of f is 2x comma 2y, and that's going to be equal to lambda times the gradient of g, which is 2x y cubed comma 3x squared y squared. Okay, so we want to set these two things equal to each other. So on the right-hand side, when we multiply lambda times our vector, lambda is going to get distributed in because it's a constant. So it gets distributed here, and it gets distributed here. And then for these two vectors to be equal, their components have to be the same. So for example, so let's go ahead and distribute in that lambda. That gives us 2 lambda x y cubed comma 3 lambda x squared y squared. But for these two vectors to be the same, their x components have to be equal, and their y components have to be equal. So this has to be equal to that. Okay, so that's going to give us a few equations that we can write down. So we get 2x equals, I'm actually going to write it as lambda in front, and then times 2xy cubed. And then the second equation is 2y equals, again I'll write the lambda in front, times 3x squared y squared. Okay, so we have those two equations. That's from setting the components of the vectors equal to each other. If we had a function of 3 variables, we would have had a third equation here from setting the third components equal to each other. Okay, so we also have one other equation to work with. And the other equation comes from our constraint, which was x squared y cubed is equal to 1. All right, so we have a system of equations, 3 equations, and 3 unknowns, x, y, and lambda. So we want to solve this system. Okay, so let's begin with one of these. So from equation 1, if we rearrange this, we get 2x minus 2 lambda x y cubed equals 0. And if I factor out 2x, we get 2x times 1 minus lambda cubed equals 0. Okay, so looking at this, it's really tempting to say, wait, can I just divide by 2x? In fact, even from the original equation, 2x equals lambda times 2xy cubed, that might have been your first thought. It might have been, oh, let's just divide both sides by 2x. So that we actually need to be really careful about. That is actually not legal. So we actually can't divide by 2x, since if x equals 0, if x equals 0 is one of our solutions, if we were dividing by 2x, we'd be dividing by 0, and that's not legal. So what happens when we divide both sides of an equation by a variable is we can end up losing a solution. So if we were to divide by 2x, we might lose this solution. And we really wouldn't want to do that. We really wouldn't want to lose a solution. So the moral there is, if you have an equation, never divide both sides by a variable. Instead, move everything over, as we did, and factor out. Because at this point we could see that either 2x equals 0, or the other term, 1 minus lambda cubed equals 0. Okay, so from 2x being 0 in this first case, this means x would be equal to 0. And if x is equal to 0, if I plug that into equation 3, then we would get x squared times y cubed would not be equal to 1. This would not be equal to 1. It would actually be equal to 0 because we'd have x as 0. Okay, so the conclusion is that means that x is not going to be 0. X equals 0 is not a solution here. Okay, so let's look at this other equation. So in this other equation, and whoops, I think I forgot to write down one of my terms. Oh, actually, I miswrote this. This should have been 1 minus lambda y cubed. Ooh, it's good we caught that. Okay, same thing here. This should be 1 minus lambda y cubed. Typically, our strategy with this other equation is going to be to isolate the lambda. So this is usually the go-to strategy in these Lagrange problems. Okay, so if we did that, if we were to isolate lambda, we would end up getting that lambda, scroll up, give myself some room, lambda equals 1 over y cubed. So you might be wondering, wait, when we did that, when we isolated lambda, we divided both sides by a variable. But you just told us never divide both sides by a variable. So there's a subtle difference there. We don't want to divide both sides by a variable if that results in cancellation of that variable. And that's what would have happened if we divided both sides by 2x. It would have canceled it away. Whereas in the second equation, if we divide both sides by this y cubed, it doesn't result in that cancellation. And why that's important is because in 1 over y cubed, I still can't plug in 0 for the y. If I try to plug 0 in for the y, it makes this undefined. But in this equation over here, if we had divided both sides by 2x, to cancel it away, if we tried to plug in 0 for the x, after that, we would have been able to. So that's why that's important. So the moral again is never divide both sides by a variable if it results in cancellation of that variable, because you might be dividing by 0. Okay, so going back to what we have here, we have that lambda equals 1 over y cubed. Now let's take this and substitute into a different equation. Substitute into a different equation like 2, because 2 also has a lambda. So let's do that. Okay, so in equation 2, we have that 2y equals, we'll have lambda here, and then times, it was 3x squared y squared. So the value we got for lambda was 1 over y cubed. And simplifying this, we get 3x squared over y. Okay, so if we rearrange this, we get 2y squared equals 3x squared. And now let's isolate for one of our variables. So if I divide by 3, I get 2/3 y squared equals x squared. And at this point, if we remember what our third equation was, in our third equation, let me scroll down so I can see it. In the third equation, we already had an x squared in this. So I'm going to substitute in for x squared. Okay, so if we do that, in this parentheses, I'm going to substitute in what x squared is. And then that's going to get multiplied by y cubed being equal to 1. So x squared is 2/3 y squared. All right, so simplifying this, we get y to the 5th. And then if I multiply by the reciprocal of 2/3, we'll get a 3/2 on the right-hand side. And to get rid of the 5th power, I would 5th root both sides. And that'll give me y equals 3/2 to the 1/5 power. That's the same thing as writing a 5th root. Okay, so I know what y is. I got to find x. So if I plug in the y value back into our equation for x squared, like this one, we end up getting then that x squared equals 2/3 y squared. So if I plug in y, we'd plug in 3/2 to the 1/5. Okay, so we'd have this. So we have 2/3 out in front. And then in the parentheses, I have a power to a power. And that means multiply the powers. So we'd get 3/2 to the 2/5. And I know that 2/3 and 3/2 are reciprocals. So this term is actually 2/3. If I reciprocal it, it'd be 2/3. I'd get a -1 power, and the -1 would multiply the 2/5, and I'd get -2/5. Okay, and then finally 2/3 times 2/3 to the -2/5 is going to be 2/3 to the 3/5, because 2/3 is technically 2/3 to the 1, and if you add the 1 to the -2/5, you get 3/5. Okay, so this is x squared. So now I need to square root both sides to get x. And when I square root both sides, I need to put a plus or minus. I'll get plus or minus, and I'll get 2/3 to the 3/5, and that needs to get square rooted. The square rooting means same thing as 1/2 power. So we get plus or minus 2/3, and multiplying these powers, we'll get 3/10. Okay, so not the nicest looking numbers because I have these fractional exponents, but still not terrible, like not too bad to write. Okay, so at this point we have our points. The closest points, this is what we were after, there's actually two of them. The x coordinate is plus or minus 2/3 to the 3/10, and the y coordinate is 3/2 to the 1/5. So if we remember the shape of our graph, so if we had our axes, and then we had that the graph looks something like this. So the graph looks something like this. It does make sense because the graph was symmetric about the y-axis. Why there are 2 points that are the same distance away from the origin. We saw that in our picture before. So one important thing that I want you to think about is we mentioned that Lagrange multipliers, when we solve that gradient sort of equation, that the points that we get might correspond to local maxes or local mins. So the question I want to ask is, why can't the points that we got, be a max? So I've just sort of stated that it's a min, but why couldn't this be a max? And I want to leave this question for you to think about. The one thing that's going to be helpful is, if we just think about a point on this curve, and I call it x comma y, and then I keep in mind what does the distance between that and the origin look like. If I call this d for distance, well, think about what that maximum distance might be. Like, where is the point x comma y on this curve, where that max might be? Or is there no max? And why? But this I want to leave for you to think about a little bit. We will sort of revisit the question about, well, how do I know if the values I got are max or min in the next video. Okay, so just to recap, in general, the local max and min values of a function that's subject to a constraint, which I'll call g equals 0, only occur when the gradient of f equals lambda times the gradient of g. And so in parentheses, I've also written, and g equals 0. So why did I write that? This is just saying that, oh, we also need to consider the constraint equation. If we remember what we did with Lagrange in this problem, we didn't just write down the first two equations that came from this gradient equation from setting the components equal. We also got to work with a third equation, which was our constraint. And that's what this means when we say g equals 0. It means you also consider the constraint as part of your system of equations. Okay, and the final note that I want to make in this video is that not all the solutions to this system of equations that I get from the gradient and the constraint equation will necessarily be max or min values. So the solutions I get, they are sort of candidates, in a sense, to be max and min values, but they don't always have to be maxes and mins. They could also be neither. And we'll explore this a little bit more in the next video in terms of when we solve these equations, How do we know whether our thing is a max or a min? Alright, so in terms of our goals for this video, we have finished our first goal, which is to introduce Lagrange multipliers and discuss how we use it to solve a constrained optimization problem. In the next two videos, we are going to do more examples. We'll look at an example in each video using this method.